In this section we want to look at the concept of work and energy and build up the ideas of energy of motion as well as energy of position and connect those up with the work being done either on the object or by the object. So we want to talk in specific about the work-energy theorem, which is a connecting relationship between the action of a force responsible for doing work and then the subsequent change in energy of the object, whether that be the energy of position associated with potential energy or the energy of motion associated with kinetic energy. First of all, we can go back and take a look at one of our old friends, the Kinematics Formula involving v squared, v0 squared, and 2ax. And let's sort of combine that with some things that we've learned here about work. So notice, first of all, we're starting with this formula, and we're going to multiply every term in here by the mass m. And all that does is take the mass and multiply it by v squared, and mass times v0 squared, and the mass times ma and x. Now let's divide that 2 out from underneath every term. That gets rid of the 2 in this term and puts a half underneath mv0 squared and a half underneath mv squared. So we have a term 1/2 mv squared equals 1/2 mv0 squared plus f times x. Notice we've substituted for ma, Newton's second law, we've substituted F equals ma times x. But we know what force times the distance is. We just defined that work was defined as force times distance. So the fact that we just have the distance x and f there is we can say, well, that is work, isn't it? Force times distance. So let's replace fx with w, and let's move the terms that are common, that are similar, the product of a half mass times velocity squared, let's move those all over to the left-hand side. So what we have here in this expression is the difference between two terms comprised of the same symbols, the half, the m, and the v squared, but the difference between the value of that calculated at one point, the original starting point, and the value calculated at a later point. And so let's define those those groupings of terms, 1/2 mv squared, as capital K, and we'll refer to that as the kinetic energy. Kinetic is a word derived from the Greek kinetos, meaning energy of motion, and so we have here the energy of motion of the object of mass m moving at initial velocity v0 and final velocity v, and the difference between those two values of the kinetic energy is attributed to the work done acting on the object m. So this is known as a work-energy theorem because it relates the work, the mechanical work done by the force F, acting over the distance x or d, and that work then results in the object's kinetic energy going from some initial value, k0, to a final value, k. So this is a cause and effect relationship, you notice, because we're looking at the cause, which is the force responsible for the work, and then that subsequent work being done on an object results in an effect that the object's kinetic energy changes from what it started with to some final value. It doesn't have to speed up. We could have the force acting against the object's motion, such as when you apply your brakes as you're moving down the road and you have a force acting against you. The work done on the car reduces the car's kinetic energy from its initial value down to some slower or lower value of kinetic energy corresponding to a lower speed. So the work-energy theorem is expressed here very succinctly as the work done on an object is equal to the object's change in kinetic energy. Pay close attention to that statement because this is a statement that relates the external agent is responsible for the work W because that comes from a force which is being applied to the object. So W is the agent responsible for this force doing the work, and the work is being done on the mass, m, that is initially moving at velocity v0. So that way you need to pay attention to who's doing the work and who's being worked upon. The work energies theorem is basically like an accounting concept of the work done on something must equal that something's change in energy. For instance, here we have an example of how fast will a 200-gram object be moving after being pushed by a 75 Newton force over 60 centimeters. Okay, in other words, we're pushing in the direction of motion, in this case parallel to the displacement of 60 centimeters with a force of 75 newtons. So the source of this force is doing work. What is the source of this force doing work on? Well, the source is doing work on the 200-gram object. So the 200-gram object is gaining that energy, and the agent responsible for this force is expending that energy. So we want to calculate, if we apply this force over a distance of 60 centimeters, how much work will that force do? Well, we know that that work is calculated by the force times the distance, so that that force will do 45 joules of work on this object. Where has that 45 joules of work gone? Well, it has gone into the object, being reflected as kinetic energy. If the object is implied to be starting at zero velocity, then that means that the object has gained, pardon me, that means that the object has gained or had a change of kinetic energy equal to the amount of work that went into the object. So that means 45 joules of kinetic energy now is the object, and that means that since that kinetic energy is equal by definition to 1/2 mv squared, we can go ahead and solve for the velocity because we know the mass of the object was 200 grams, or of course 0.2 kilograms. Don't forget that we're always, even though problems may be stated in grams and centimeters and feet and inches and whatnot, you're going to want to express your answers and convert all your numbers to the meter, kilogram, second units as you put them into the relationships that we're developing. Okay? And as a result of that 45 joules of kinetic energy, the object will attain a velocity of 21 meters per second. Probably somewhere around 46, 47 miles per hour. So, as you can see from this example, that again, the concept is that an external agent acts on an object, the object gains energy as a result of the external agent's work done on it. If you think back to the external agent, it could be you pushing something, it could be a string attached to it, pulling on it. It could be a spring that has been compressed, and then as that spring expands, it pushes on an object. Could be a non-contact force, such as gravity, acting on an object. And so whatever it is, the agent is the force. The force does work, and the object that's being acted upon is the object which gains the energy as a result of the work. Here we have another example of a car that speeds up from 10 kilometers per hour to 20 kilometers per hour, and we're told that as a result of that increase in speed, it was because 5,000 joules of work was done on the vehicle. So look at that as beginning information. We know something about this vehicle. We know that it takes this 5,000 joules to make it go from 10 to 20 kilometers per hour. So based on that information, we want to know, well, what if I wanted to go from 20 to 30 kilometers per hour? How much work would that take? In other words, I am going faster at the beginning, but I'm increasing to an even higher velocity And would it take the same amount of energy to do that, or would it take more, or would it take less? Okay. Well, first we're going to start out with what we know. We know we have 5,000 joules of work, and we know the result of that is our velocity increases from 10 to 20, right? And therefore, the work energy theorem can be used because we know on the left-hand side we have 5,000 joules. On the right-hand side we have the 20 kilometers, which is 20,000 meters, and 3,600 seconds is the time in 1 hour. And so there's the velocity squared at the end when we're going 20 kilometers per hour. And of course this term is the velocity term involving the 10 kilometers per hour. Notice I've simply converted the numbers, the kilometers and hours, right in place rather than do it separately and then bring it into this problem. You can do it either way. Now notice that the thing that's we're missing here is the mass of the car. Now right here, that's mass. Don't confuse this symbol here. That's the unit meter, whereas that's the mass of the car. So we need to solve this problem for the mass of the vehicle, which is what we would do. Find out the mass. Then you can use that mass in the calculation to find out the work it would take to speed up from 30 kilometers per hour from 20 to 30. And we need to know the mass right here in this problem there and down here. So that mass is going to come from the fact that up here we knew how much work it was, so we can solve this equation for the mass, factoring out the mass here and here, and solve for that mass, and then bring it down here. I'll leave that for you to do. You need to be filling in the blanks on these problems that we don't complete. And you'll find out how much work it takes down here. So it takes 5,000 to go from 10 to 20. How much does it take to go from 20 to 30? Okay? Now, kinetic energy is energy of motion. That's the energy we just studied. If an object is moving and it possesses mass, then it has kinetic energy. And we calculate that kinetic energy by the product 1/2 m, the mass, times v squared. And that kinetic energy can change because work is done on the object to make it speed up or slow down. And as a result, the object's velocity changes, its mass doesn't change, as long as we're dealing with a non-relativistic motion, which is meaning motion that is not approaching the speed of light. So, that's one form of energy. Now we want to talk about energy of position. And this is known as potential energy. The word potential is a word which means not really evident. Okay? It's not manifesting itself in any manner. It's potential. It's something that's going to be evident later on or as a result of some circumstance, but clearly at this point it is just a sort of waiting energy. And by this we mean if you were to take a book from the table and lift it up and hold it in your hand above the table and ask the question, does the book possess energy? It's not moving. Now, you'd say, well, by definition of kinetic energy, it doesn't possess any of that. It's not moving. However, if you were to, say, let the book fall, you would note that it picks up speed according to our normal one-dimensional free fall, and its velocity increases. And if it were to strike the table and you had an egg on the table, it would crush the egg, and it would do work on the egg, wouldn't it? In other words, the fact that it did work on something meant that it did possess energy, and we know that the energy it has when it's falling is kinetic energy, but did it possess energy when it was not moving before you released it? And a very important principle is that energy cannot be created nor destroyed, so if it had energy as evidenced by the kinetic energy of motion, as it was falling, right, then that energy, then it had to have energy when it was not falling, energy that wasn't evident. And that's what we refer to as potential energy. And that potential energy is the result of the mass, the book, for instance, being held in a field, a force field, in this case, the gravitational field, at a position such that if the object is released, it will change its position and increase its kinetic energy as it falls. So there are various forces that we can use to define several potential energies we're going to use. The gravitational force, which, as you know, we've studied this a little bit in the chapter on Newton's laws. The gravitational force results in a mass having a weight, and the weight of an object is the mass times g. So that's the force of gravity on that mass. Okay? And so that force of gravity, whether the object is moving or not, is acting on that mass. So the gravitational force, if you hold a book 1 meter off the floor, the gravitational force is acting on that mass, and the value of that force is mass times g. If you release the book, then the gravitational force will do work on the book and move it, act on it, through the distance that it falls. As a result of that work being done, the mass increases its kinetic energy from 0 to whatever the final value is when it strikes the floor. The concept of potential energy is that the object had to have had potential energy before it was released, and that energy became converted to kinetic as it was falling as a result of the position of the object above the floor, which we'll treat as our reference point. In other words, objects residing on the floor will be thought of as having 0 potential energy. Objects then lifted above there will have positive potential energy, and if you have a hole, objects below the floor will have negative potential energy. And all that means is that the gravitational force acting on that mass will do positive work on it if it is above the floor, and it would do negative work on it if it was below the floor, because the direction of the gravitational force is downward, and if that's the direction of your displacement, then our work definition, F cosine theta times d, that will be positive because the downward force of gravity and the downward displacement are both in the same direction, and so the work done by gravity will be positive on the object. If you're in a hole, you're not going to fall out of the hole. You would have to reach down and pull the object up. You would exert a force upward against the pull of gravity, and the displacement would be upward. And so gravity is pulling down, but the displacement is up, so the cosine of those directions is 180. Cosine of 180 is negative 1, and therefore gravity would be doing negative work in an object. Gravity is not actually raising you out of the hole, are you? Now, so the potential energy is an energy associated with the position of the object for gravitational, and the same thing with respect to the spring. The spring stores energy as it is compressed or extended. It stores that energy in the form of the stress in the bonds within the material, and it's expressed for us in general by the spring constant K. So that the spring constant K tells us how much force it would take per meter to extend a spring as well as compress a spring. So that means that the spring is actually storing energy, and the more you compress it, the more energy it stores. The more you extend it, the more energy it stores. So it is position dependent. It's dependent upon the amount of this variable x, which is its position or its extension or its compression. So we're going to use the symbol U to represent potential energy. And the units for that potential energy, of course, are the joule unit, which is our typical unit for work and energy. Now, we can calculate potential energy for these two forces, the gravitational force and a spring force, by the following definitions. First of all, we know that the work it takes to stretch a spring from an extension x0, in that case it took 1/2 kx0 squared to get that spring stretched to that point, and if we stretch it to a further distance x, it's going to take that much more work to stretch it from 0 to that point. So the amount of work needed to change the spring from x0 to x squared to x is given by the difference in work from where you start to where you finish. And then therefore that represents the amount of energy stored in that spring as a result of that change in its extension. Now, generally we treat this term here, where x0 is the equilibrium length, we say, let's let that be 0. In other words, the spring doesn't store any energy in it when it is not compressed or extended. It's just sitting there. But when you compress it or extend it, you have to do work on it, and the work you do on it is stored as potential energy in the spring. Similarly, the gravitational field, because it is a force field in which the force of gravity is m times g, then the potential energy is going to be dependent upon the position y above the ground, and the potential energy available is going to be the result of the difference of the potential energy available at one position to another. Now, y0, again, we could choose the ground or the floor as our reference level and say anything on the floor has a potential energy of 0, and then anything we measure above the floor has a positive potential energy given by mg times y above the floor, or if y is negative below the floor, mg times y as well again. So these are the definitions we'll use for potential energy for a spring or a gravitational field. So here we see an example. We have a floor, okay, ground level, basement level at -3 meters below ground level, and then the second floor above ground level at 4.5 meters above that. So those are our reference lines. We're going to define the ground level as be the place where the potential energy is 0. In other words, mgy equals 0 at this point. Okay? We're going to then calculate that the potential energy at a position 3 meters below the reference level will be mg times -3. And likewise, the potential energy at 4.5 meters above ground level will be mg times that 4.5 meters. So there's not a problem with having a negative energy, because in this case that negative energy just refers to the fact that we have to start with some reference point where we're going to say it's 0, and anything below that would be negative, and anything above that would be positive. Don't misunderstand, the kinetic energy term 1/2 mv squared can never be negative, because v squared will always be a positive number and the mass will always be a positive number. How about this example? How much energy, how much would you have to stretch a spring whose spring constant is 45 newtons per meter in order for that spring to store 1 joule of energy, right? If we know that the potential energy stored in the spring is 1 joule, we know its spring constant is 45, what value of x will we need to impart on that spring in order to store that amount of energy? The potential energy of the spring is defined as 1/2 kx squared. Again, with the assumption that the the term 1/2 kx0 squared is set equal to 0 because the equilibrium length is where the spring doesn't store any energy. So we can rearrange this, solve for x. We get square root of 2u over k. And notice that plugging in your values, you find 21 centimeters as the amount you would have to stretch this spring in order to store 1 joule. In other words, this is a spring that is stretched by approximately 9 inches, and it will store 8 to 9 inches, and it will store 1 joule of energy. Remember that the stiffer the spring, the higher the value of the spring constant. So a very mushy, sort of floppy spring will have a very low value of spring constant. A very stiff spring will have a very high value of spring constant. And this is true whether we're talking about the helical springs or whether we're talking about leaf springs. We're really talking about the ability of that substance to be deformed or be subjected to a force and to return to its shape once the force is removed. As we know, you can't subject all substances to an unlimited amount of force and have them return. However, our expression for Hooke's law is called a linear elastic expression, and it means that we are maintaining a limit on the amount of force we can actually put on this spring. As you know, if you just started to pull a spring and you just stretched it as far as you possibly could and just kept going, ultimately it would not spring back to its original shape if you release the force on it. Well, we're not going that far. We're going to maintain the limit that we are not going to stretch our springs beyond their elastic limit, it's called. And so that if you stretch a spring by, in this case, 21 centimeters and release the force, it will go back to its original length.